Hello, everyone. Thank you for being here today. My name is John Stratton. I'm the Chief Technology Officer here at Multicoreware, and I want to welcome you all to this presentation, this session, where I plan to talk about some of our perspectives here at Multicoreware about how we approach software performance from a productivity-oriented mindset, which I think is an important but somewhat overlooked area of total solution performance. So I will be taking questions in general. If you use the Zoom meeting features to send questions to the moderators, we will have a Q&A period at the end to go over anything that you'd like to discuss more by the end of the presentation. But for now, let's go ahead and get started. So as a high-level outline of what we're going to do, I'm going to start by introducing something that I call the productivity curve, which is less of a technical piece of content and more a framework for understanding how do the performance of a software system and the productivity of developers interact and relate to each other. Once we've got that framework established, we'll talk about some conceptions and misconceptions around performance optimization and productivity. We'll go into some case studies about how productivity can actually increase performance of a given system, and then some allusions at the end to some ongoing efforts we have at Multicoreware to continue to increase performance through productivity efforts overall. So I want to introduce, as a starting point, this idea of the ideal productivity curve. So the ideal productivity curve is just a relationship between how much development effort are you expending, and this could be an individual if you're looking at it on a single individual scale, or it could be a team. Development effort is a very difficult to measure thing, and it's generally loose, but I think we all understand kind of what we're talking about there. And then we look at the performance of the solution that is developed at that point in time with that much development effort invested. And I want to call out a couple of things about this graph that I think relate to our ideas and conceptions about how software development works. So first of all, at kind of the bottom left corner, we all expect that there's going to be some initial development effort to get your first minimum viable product, your first prototype, the first version that is functionally correct in terms of your overall application. And then it's going to have some initial performance the first time you get it implemented. It's going to have some performance when you deploy it and run it on a given system. And then obviously over time, the more effort you spend on improving the performance of the system, the higher performance is going to get within reason. We understand that, all systems have something that we call peak performance. There is some ceiling that you cannot exceed when you're working towards improving performance. And our goal is not to exceed it, given the individual systems constraints. Our goal is just to get as close as we reasonably can to that peak performance that we're aiming for. And you'll notice that this curve is, well, curvy. It's got a couple of points on it that I want to highlight here. One is, once you've gotten your first functional prototype, often a little bit of development effort gets you some pretty significant performance improvements. This is what you might call the low-hanging fruit. There are things that you can do often at the beginning of a performance optimization project to get performance increased very quickly with not that much effort. So you've got low-hanging fruit in the early optimization times, but then the more time goes on, it takes more and more development effort to get diminishing returns on your performance improvements, again, keeping things like the system that you're running it on constant. So hopefully this gives you kind of an idea of what the productivity curve is about. It's just the shape that relates how much development effort you've spent to what is the performance of the software system that you have at that point in time. And it's got some features that I think we all relate to in terms of our real world experience with low hanging fruit in terms of performance optimization early on. And then the better your performance gets, the more work it takes to further improve performance. Okay. So, what about productivity? Well, the way that you want to think about productivity is a scaling factor or a adjustment to development effort. If you take your development effort and you increase productivity, effectively what you're doing is shifting and scaling this performance curve. You're shifting it to the left where the same development effort gets you increased performance results because you're more productive. You effectively get a larger multiplier on your development effort than you did before, which means for the same development effort, you can get a higher amount of performance. Okay, fairly straightforward. When we start applying this into real projects that have to be executed, on time and within budget and things like that, there are a couple of scenarios that I think we should understand. The first one is this idea of time to market. So for time to market, often one scenario that you might have, which happens fairly often, is you've got some kind of product, whether it is a real-time video processing system, a real-time inference system, whatever it is, there is some development effort performance curve for that particular project. It's going to take some amount of development effort to get some amount of performance, but your product has some minimum viable performance. In order for the product to be successful in the marketplace, it has to hit a certain performance metric in order to handle real-time video in the system that you're deploying or something similar. Maybe this is the minimum viable performance that you need in order to be competitive with the other systems or products that are out there in the market already. Okay, given that your product has a minimum viable performance and this is what your productivity curve looks like overall, that productivity curve is going to tell you how much development effort it's going to take in order to reach that minimum viable performance. And that gives you your time to market. This is how long it is going to take you to develop the software system to the level of performance needed to be viable in the marketplace. That determines your time to market. Well, what happens when you increase productivity? Well, if you increase productivity, then that curve shifts over and your time to market has now been reduced. You've gotten a faster time to market based on the increased productivity of your team and the system overall. And this, I think, kind of makes sense. You expect things to go faster. If you're trying to hit the same target and you find some way of improving the productivity of your team, then you can get to market faster. That is the more obvious and the more straightforward approach of productivity as it relates to performance. There's a second scenario that is equally valid, but I think is a little bit more overlooked. And it has to do with, again, what happens on this curve and what happens when the curve shifts due to increased productivity. So let's say that instead, we look at a scenario not of there's some minimum performance target and we're trying to hit it as soon as possible, but instead, let's just say we have a product that we are investing ongoing development effort into. You've got a team of people that are working on this product and you've got some next release date planned. Well, given where your next release date is and given how productive your optimization team is going to be, again, this productivity curve is going to get you a data point which says this is the performance that you're going to get on release. If you invest a certain amount of effort before the next release date, this is the performance you're going to achieve. What happens in this scenario when you increase productivity? The curve moves again, and now what you see is that given the fixed release date or a fixed amount of development effort that you're willing or able to expend on the project, what you get is a performance gain. Increasing productivity in an environment like this actually gets you more performance of your product on release by increasing the productivity of your team while they are working on the performance optimization of that product overall. So perhaps a little bit non-intuitively, productivity enhancement in this idealized scenario can deliver increased performance. So I hope that covers the core idea of the framework that we're going to be using for some of the later discussions. This idea of a productivity curve, some curve that relates how much development effort you need to expend to get a certain level of performance, and then how shifts and adjustments to that productivity curve can influence both the amount of time it takes to reach a certain performance goal or the amount of performance you can get for a given development effort. Now, obviously, all of this is based on an idealized productivity curve. In reality, things are more complicated and there are more choices. So let's say that you are developing some kind of digital signal processing application. The first thing that you might do as you're prototyping is develop a MATLAB implementation because it's got a robust set of libraries and a very easy interface for the mathematical implementations of these kinds of digital signal processing algorithms. If you stay within MATLAB, you'll get one productivity curve. It's going to be very easy to prototype, but as you invest more development effort, you can increase the performance of the MATLAB code natively, but at some point you're going to run out of road. Like there are fundamental limits to how efficient you can get raw MATLAB code to behave to perform on its own. So when you go to deployment, often you're switching to a different programming language, a different development environment for higher performance in your deployment scenario. If you just stick with vanilla C as a programming language with loops over scalar data items, again, you should get some kind of productivity curve. It's not as easy or as quick to implement as MATLAB. You should expect a higher initial investment to get your first working prototype, but you should expect higher performance initially, and you should be able to work on improving the performance of that C code over time to significantly exceed the performance of your original MATLAB code. But obviously, we're deploying on complex systems with complex instruction sets built to deliver performance. And maybe the compiler tools aren't able to give us every bit of performance that should be possible out of that hardware system. And you may need to switch to writing your code in assembly in the worst case, or more likely things like vector intrinsics or higher level vector programming interfaces for a digital signal processor or a CPU. Well, if you go that route, again, it is going to be a higher development in effort in order to get your first working version according to this paradigm. But then the more performance, the more development effort you invest, you can exceed the performance of what you would have gotten in C by itself. So given that you've got all of these productivity curves available, what do you actually do in a project? Well, given that each implementation approach has its own productivity curve, you ideally would want to pick which development curve you want to be on at the beginning that will get you to the performance target you need with the minimum development effort. right? That's kind of how we would approach it. And we use our professional experience to get a good sense of which curve is most likely to be able to get us to that performance target with a reasonable amount of development effort. So given a, given some target performance, there will be a correct solution to say, oh, well, for this level of performance, the least development effort to achieve that performance, given these productivity curves, is going to be sticking with C and just continuing to improve the performance, working with the compiler to make sure that you enable auto vectorization as best as possible. But, we could have gone straight to assembly or vector intrinsics, but the development effort to get the same level of performance, if we knew this ahead of time, we would say, that's going to be too much effort. If this line shifted up, then that calculus would change. We would, if the performance requirements shifted up, we may decide earlier to go for assembly or vector intrinsics. If the performance curve shifted down, we might say at some point, actually, let's just stick with C or like an automatically converted version of the MATLAB code to C, which will be good enough. So we know that these productivity curves are real. And because they are real, for a known performance target, there should be a correct approach for the fastest time to market. The problem is that's not how real projects work. So real projects work something like this. You've got your performance target, and you've got your initial MATLAB code. You've maybe spent a little bit of time improving the performance of the MATLAB code just to make sure that the algorithms that you're using are, efficient and straightforward. But this is all of the information that you have at the moment. You don't know with definitive certainty what the productivity curves of the MATLAB version going forward or the other solution alternatives will look like. You've only got predictions based on past experience and professional wisdom. So maybe at this point you predict that, well, I could keep improving the performance of the MATLAB code, but it's not going to get me to the performance target that I want. Let's go ahead and migrate to C. So you migrate to C, you spend some development effort. You don't do all of the optimization effort in MATLAB. You say, we're going to bail on that earlier so that we can get to market faster. You start with your C implementation, you get your first version, and you spend some amount of time optimizing C, but you're starting to get diminishing returns. And now you say to yourself, maybe if I keep investing in C, I could reach the performance target, but I know that the ceiling's going to be higher on assembly or vector intrinsics anyway, so let's go with that. And so you reinvest development effort, and sure enough, you reach your performance target with more opportunity for performance growth after that if you wanted to keep optimizing. But the problem is you, at that point, are making that decision without knowing what the rest of the performance curve on C looked like. And maybe, in fact, if you had just kept developing and investing in C, you would have hit your performance target sooner. It's really hard to do that. It's really hard to know whether your current optimization efforts will reach a certain target with a certain amount of development effort, or whether an alternative is going to give you a faster route to get to that ultimate performance. So we all know, I think, from experience that performance prediction is hard to do. It is really hard to predict how much work it's going to take to reach a certain performance target, except in hindsight. And this leads us to say, well, then how useful is this productivity curve in general? I want to spend some time now talking about some common beliefs about performance, which are at least somewhat justified, but may not be as universally applicable as we think. So one common belief is that languages and systems to improve productivity are performance neutral at best. And there's a good justification and reasoning for this. And the reasoning is, well, any optimization that you could do at the higher level could also be done at the lower level. Any optimization that you could do in C could be done in vector intrinsics or assembly. Any optimization that you could do in Python or MATLAB could also be done in the C or C++ or Fortran. So there should be no performance benefit of trying to go with a higher productivity approach or system overall. Common belief, reasonably justified, because obviously the peak performance should not be better when you get more productivity. Another belief is that languages and systems, to improve performance, are going to be productivity neutral at best. And this is kind of the efficient market hypothesis that says, well, the default method, the state of the art, is already the path of least resistance for the performance that you get with that path. And this also makes sense. If you look at languages like C and C++, they are already well refined. They have decades of history built into them. And if you want to exceed the performance of those languages, you're going to have to do more work and invest more effort to do something like vector intrinsics or use multi-threading or accelerated computing programming models, which will take more work and be more difficult to use than C and C++, but should get you better performance when you do. So again, this is somewhat well justified based on our professional experience with a lot of systems. Going back to the productivity curves that we just talked about, there's a common performance belief, in my opinion, that investing time in high productivity environments is kind of risky because you might have to redo all of that work when they fall short of performance targets. If you know that you've got a certain performance target and you're not sure whether C version of the application without doing intrinsics and assembly level programming is going to get you the performance that you need, you may not want to spend the development effort to optimize your vanilla C version because if you end up needing to switch to intrinsics, all of the effort that you expend trying to improve the C code on its own is just going to make more work for you when you try to convert over to the vectorized version, if that ends up being what you need to do to reach your performance target. So again, reasonably justified hesitation there. So given all of those hesitations, I want to talk about a case study. When we started working on this project, this is more or less what the productivity curve looked like for the Cadence Vision P6 digital signal processor. There were other options, but for now, let's just consider these two. There was an OpenCL stack available for that accelerator. And then there was Halide that was out there. You could use the OpenCL backend of Halide, and the OpenCL backend of Halide played fairly nicely with the OpenCL stack of the DSP, which was nice, and Halide was certainly easier to use than the OpenCL framework for developing applications. But the performance and productivity curve, productivity curve looked something like this. Halide, very easy to use, very low peak performance capability out of the box. OpenCL, much more initial and total development effort across the board, but much higher peak performance that you could achieve as a result. So this was the scenario that we walk into initially. And to give you an idea, here was a collection of benchmarks that we were using to evaluate the system. You'll see it's focused on image vision processing operations, which makes a lot of sense. The best that we could do on the out-of-the-box version of Halide connecting with the OpenCL stack from Cadence at the time, we could in some cases get maybe a third to half the performance of the OpenCL version if we were lucky. And in a lot of situations, we were stuck with a fraction of a percent of the performance that you could get with the OpenCL version of the same operation, the same kernel. Okay. Given that context, what is the right solution here? What would you think about or do in this scenario? Well, if you're pulling in some of these concepts that we have about performance and about productivity, you might say to yourself, languages and systems to improve productivity are performance neutral at best. So sure, we could improve the performance of Halide overall, but remember, the Halide is just generating OpenCL code. So there's no optimization that we can do in Halide that couldn't be done directly in the OpenCL code itself, which means there should be no performance benefit to improving Halide. Sure, you might get a productivity benefit, but in terms of total performance, there's no gain to be had here. At best, you can maybe hope to break even if you're lucky. That is a perspective that you could take. You could also say, oh, and remember, because Halide is meant to be a higher productivity programming language or environment, it's always going to be risky because you might have to redo all of that work when you fall short of performance targets. And again, this goes with the assumption that the default method, OpenCL, is already the path of least resistance for the performance that you're going to reach. This is one perspective that you could come in with, and I think a lot of people do come in with. We would challenge that idea, though. This way of thinking basically assumes that the state of the art is the best that it's going to be, which doesn't really leave room for the idea that what are the real opportunities for improving the state of the art? I don't think that we've gotten heterogeneous programming and software performance optimization solved as an industry right now. And I think that there are lots of opportunities to improve the state of the art, both for performance and for productivity. So it turned out in this case, we were right, and we were more right than we thought we would be. So we did improve and extend Halide with some necessary features. The reason that Halide was preventing us from getting the performance that we needed was it just didn't have necessary optimization features to deliver performance on the digital signal processing environment. So we made some small extensions to Halide that allowed the users in Halide to do and express those kinds of optimizations. And in the end, there's a lot of things to call out here, but the big conclusion is that this middle line here in blue, with the blue hash on the bar chart, is our ultimate Halide solution. And on average, our Halide implementations beat the OpenCL implementations in practice. It wasn't consistent. Certainly in many cases, the OpenCL code was a little bit better than the Halide code, sometimes significantly better than the Halide code. There were also times that the Halide code was significantly better than the OpenCL code. And you should be questioning yourself here, because we already know and we already established that no optimization that you can do in Halide is unique to Halide. Every optimization that you could have done in Halide could have been done in OpenCL. So how did we end up with better performance? Here's what happened. By shifting the productivity curve, the OpenCL versions that we were comparing against, this isn't the OpenCL version that got peak performance. What happened was there was a developer team, primarily in Cadence, that was doing optimization of their OpenCL example kernels, And they said, let's put in a reasonable amount of development effort to get a reasonable amount of performance out of these kernels. And so that's what they did. They had some bar that said this is a reasonable amount of development effort. We noticed that we're getting diminishing returns for our development effort and optimization effort in OpenCL. The performance seems good. We'll call it there. Obviously, before we started, you could expend the same amount of development effort in Halide, but because of the technical limitations, you had a performance ceiling and weren't going to get anywhere close. But we were able to shift the performance curve for Halide such that for the same development effort, you actually got a higher level of performance. Why? What does that mean? The performance that we got in Halide was due to the fact that because Halide was so much more productive, we could try and test a much larger number of tiling factors, unrolling factors. There were many more optimization configurations that we could just try and test. In OpenCL, each configuration that you test takes a significantly larger amount of development effort to test and try. And so you hit diminishing returns earlier and you say, sure, I could try more configurations, but it's going to be a lot more work for each new configuration. And the likelihood of me getting a performance improvement keeps getting smaller and smaller. So let's just call it there. In Halide, since the development effort required to test a new configuration stayed very low, the productivity curve was shifted significantly to the left. For the same development effort, you could try more configurations and find the higher performance optimization configurations. So true, it is still true that in OpenCL, the peak performance of OpenCL is never lower than the peak performance of Halide. But where these performance curves are shifted, there is a significant range where now the development effort required to get a certain level of performance is better than Halide in a lot of circumstances, even though there are circumstances where Halide peaks out. And yes, OpenCL gets you better performance if you find the optimizations that you can do in that area that you couldn't have done meaningfully in Halide, again, because of some of the technical limitations. So I just want to call out here that this is an example where our conventional wisdom about performance and productivity should be questioned and challenged at least a little bit. This was a situation where a higher productivity language actually enabled a team to get higher performance results, not because peak performance improved. Obviously, that's impossible. But because the performance that you could get for a certain amount of development effort was improved, and because of that increase in productivity, a reasonable amount of development effort actually got you better performance than a reasonable amount of development effort in an alternative, lower productivity, but higher peak performance environment. So with that, I want to talk some about projects that we're working on now to continue playing in this space of what does it take to achieve a certain degree of performance with a certain amount of development effort. And one area I want to talk about here is Valve. It's a variable length vector library, kind of built on the assumption that there are new technologies, especially in CPUs now, that need a degree of support that we haven't had to provide before. Notably, ARM v9 with the SVE instruction sets and RISC-V with the RVV instruction sets. These are different versions of vector instruction sets than we've been used to dealing with. They're not as well supported. And the question then is, okay, well, what should we do? Some applications require manual vectorization to get sufficient performance. So we're assuming that auto vectorization doesn't always reach your performance target. basic enablement for any of these systems will allow you to reach manual vectorization targets with assembly programming or with intrinsics. Those have been supported and available. But there's kind of a gap in the performance, and there's a gap in the performance curve where doing these kinds of manual vector intrinsics is actually a lot more effortful than the vanilla C or C++ code that you would have been starting with. We are working on a product called Valve, which is going to enable the same kind of manual vectorization. So you're still doing explicit vectorization in your C and C++ code, which means it is going to take a little bit more effort than vanilla C or C++ code. But the idea is that it should be meaningfully better in terms of performance because you're giving the compiler significantly more information about the explicit vector opportunities. And it should be much easier to program compared to intrinsics because the syntax is just much more similar to the scalar pointer code and object and element-oriented programming that we're used to doing. So this is one way of describing it with words and examples, but if we relate it back to what we have been talking about earlier, basically our value proposition, if you put it on this productivity curve framework, is that, well, if you're just doing C and C++ in the auto vectorization regime, there's some amount of performance that you will peak out at with only relying on the compiler to do manual vectorization, auto vectorization, for you. And then there's a big gap between there and the effort that you have to do to either write your vectorized and optimized code in assembly or intrinsics. And the whole point of Valve is, again, we're not going to beat the performance of assembly or intrinsics because obviously the library is just a higher level interface on top of those same assembly code operations and intrinsics. And it's never going to be faster and more efficient than just writing simple C and C++ code, but it can fill out this region of the productivity curve where if your performance target is somewhere in this realm, this product will allow you to reach that performance target with much lower development effort than you would have needed otherwise. So this is one area that we're investing in as a company. The other one that we're looking at moving forward into the future is productivity and deep learning. Obviously, people care a lot about deep learning efficiency and deep learning applications. There are lots of exciting things going on there. But if you look at the landscape overall, if you care about the performance of these systems, you've got high-level frameworks for model development, which are the productivity environments. You've got low-level tools for hardware-centric profiling. Think of Insight on NVIDIA. Every AI accelerator is going to have their own tool in this area that gives you very low-level information about what is going on the hardware platform. And there's relatively limited support for anything in between. How do you go about improving the performance of your deep learning model without going all the way down to the very lowest level details of what is going on in a hardware-centric approach of profiling? NVIDIA does have some pretty good tools in this area, but they aren't generalizable. There are a lot of other AI accelerator companies out there, and obviously in the data center, NVIDIA dominates, but we work as Multicoreware, we work a lot on the edge as well. And in edge environments, NVIDIA is not the only player. They're not even necessarily the predominant player in a lot of automotive and mobile environments. You're working with other accelerators, digital signal processors, other custom inference engines, things like that. And the problem is, well, if you look at the model efficiency curves right now, you've got one curve for NVIDIA where they've invested a lot in productivity and they're pretty good in terms of efficiency. And basically, all of the other AI accelerators out there right now, I would say some of them, I mean, in order to compete with NVIDIA, you have to have higher peak performance on some metrics. So that's going to be a given. But right now, the productivity is not there. The amount of development effort you need to get your model deployed on these these other AI accelerators and to reach a certain performance target is larger than the development effort required to get the same degree of performance out of NVIDIA until you get into this regime where their peak performance starts to overtake NVIDIA because they're doing some more custom operations there. So for us, we're looking at this environment and saying, what are the opportunities? Certainly, there are opportunities to improve the performance, help people follow the productivity curve in the NVIDIA ecosystem and get better performance on that existing hardware platform. But there are also a lot of opportunities there if we were able to shift the productivity curve for other AI accelerators. We could start making the ecosystem and the development environment a lot more interesting and competitive if we could get the productivity curve for other AI accelerators shifted over to the left. So that is something that we're openly working on right now. It's too early to talk about any specific products that we're going to be releasing at any particular time. But if this is an area that other people are interested in, we are actively working in this area and looking for partners and collaborators in this space overall. So some closing thoughts to wrap up in general. One, productivity is important for solution performance overall. The main thing I want to convey is to remind everyone and remind all of us, because we often don't think about it, but productivity limitations in a system are just as much of a threat to total solution performance as system deficiencies. If we're not getting the peak performance that we expect out of a system, that is a threat to the viability of a solution on that system. But just as much of a threat to the viability of a solution on that system is the productivity limitations and how much development effort it's going to take to reach our performance targets on those systems. The flip side of that, as illustrated by the case studies that we talked about, performance optimization productivity is just as important as system peak performance for total solution performance. Yes, the higher the system peak performance is, the more headroom that you have to be able to reach your performance target. But the productivity that you have and how easy it is to reach some meaningful fraction of that peak performance is a major contributing factor to the total solution performance that you're going to end up with, given limits to how much development effort you will be able to invest in a system. The value of productivity, I think, is typically underestimated. Yes, we know it and we think about it, but in terms of quantifying it, it's actually pretty hard. And we'll talk about that in a little bit more in just a moment. But just to think about the value of productivity, if a tool or a library increases the productivity of one US-based software engineer by 10%, especially if they are a more senior developer, that's like a $10,000 a year value. How much are we often willing to spend on tools for productivity? I know if I looked at, $10,000 for a productivity tool, that's a lot more than I would normally be willing to spend. And even if I thought it was justified, I know that I would have a hard time convincing my CEO that this was a worthwhile thing to spend on. $10,000 just for a tool when you could do that work yourself. That's a hard ask. But if you look at the value that we get from increasing the productivity of our limited developer environment, that can actually be significant. And that's something that we all have to think about and work on to say how much value are we getting out of our productivity tools, and are we undervaluing them? Should we be adopting them more than we are currently? One of the reasons that I think we undervalue them is actually that it's really hard to measure and develop productivity tools. Designing systems and tools for productivity is challenging for those of us with a computer systems background. We're used to being able to put down quantitative performance metrics that we can hit and measure easily. The problem is that productivity is much more about user experience and product design, which is not generally the expertise of people that are designing systems or doing performance optimization on systems. They're also really hard to quantify because you can't just plug in a system, run a benchmark, and see what the result is. Quantifying productivity is an area that requires more social science experimental methods. You have to get a group of people, try something, measure how long it takes them to reach a certain goal, and then do statistics on that, because it's a really noisy system and a really noisy signal to try to understand how much productivity gain did we actually get out of this system. We have like gut feelings about these sorts of things, but gut feelings don't translate to CEO business sense very well. And coming up with quantitative measures of these systems is a challenge. It's something that at Multicoreware we are working on, but it is a challenge overall. So that is where I wanted to end with closing thoughts. This is not easy work to be done. It is not an easy way of thinking about things, but it is critically important that we take into account productivity when we are imagining the work of software performance optimization and delivering high performance and efficient systems into the marketplace overall. So that is my last slide. I want to thank you all for your attention. And at this point, I will call in our moderator to see what questions we have, if any.
Hi, John. Before we proceed, thank you very much for your closing thoughts and your presentation. This is an invite for any questions that you may have. You may pose those questions to me directly or in the group chat or to John directly. Yes, John, we have a question right now. Why does the new designing systems need a creative human touch?
It needs a more creative human touch because performance optimization is a human activity. We're not talking about the era 20 years ago when I would say the predominant mindset was you had two camps. You had either the camp that said the programmer is not going to help us at all. In order to improve performance, we must wring performance out of an uncooperative programmer and an uncooperative programming environment with no effort or support from them. Or on the other side, you said you had high performance software developers that said, I don't trust the productivity tools or the compilers to do the optimization work as good as I could. I want them to get out of the way so that I can do my optimization work manually and not trust the tools in the software system. We're in an environment today where I think those two, that dichotomy between programmers will not help improve performance, so we have to get it without their help, or tools will not help me improve performance, I have to have the access to do all of the optimization myself and get the tools out of the way. I think people understand now that there's more of a spectrum and a space between these environments where developers and tools need to be able to collaborate with each other. there is now a much larger group of people that need to care about software performance, um, because we're not getting it for free. And because more of us need to care about it, we'd like to do it as efficiently as possible. We'd like to our work to we'd like that our work on improving software performance would be as efficient and productive as possible. And we are happy and interested in working with tools to achieve that. And on the flip side, tool developers, you can say, well, if I'm going to develop a tool to improve performance, now performance optimization is a human activity. There are people working to improve performance, and you're not designing a tool to operate in the vacuum fully automatically. You're designing a tool that's going to be used by people and work in collaboration with people. And so this is now like a product. The software developers are users of these tools that have to have a good experience and a good return on their development effort investment in order to get the productivity collaboration that we want between the people that are designing tools and systems and the people that are using them and want to spend effort improving performance.
Thank you, John. And thank you, Shrisha, for that question. We now have an anonymous question. The question is, how can I evaluate Valve for my work?
Right now, if you go to the Multicoreware website and submit a contact request, we will be happy to release an evaluation version of Valve for you to test and try on your own. We're in the process of developing something that we could safely post to the public website without losing too much of the IP value. But if you just want something that you can download the test, wait a couple weeks and there should be something online. If you're eager to try something out sooner, go through the contact form on the webpage and someone will get back to you.
Thank you, John. That was an anonymous question. Let's move on to the next one. We have one more question. If you could explain the concept of code refactoring, how does that contribute to software productivity and maintainability?
So I haven't been focusing very much on maintainability because there's a lot to be done just in improving performance. This is In this presentation, I've mostly focused on the relationship between development effort and performance, but there's also a sense in historically performance optimization has been viewed as antithetical to good software design, where you keep your software simple, simple, nicely modularized, and following many good software design principles. But then if you care about performance, you basically have to throw all of that out and throw out all of your design principles for good software design for robustness and reliability in order to achieve performance. I think that's also a false dichotomy, but it is something that can be in tension with each other. If you've gone through the design of a software system not worried about performance at all, you are going to make design decisions that hurt performance that are then going to have to be refactored and redesigned in order to meet your performance goals. But I don't believe that if you thoughtfully plan for performance in your design process, that you can't achieve many or all of the goals of good software design in terms of modularity, code organization, abstraction, and still reach the performance targets that you want by making sure that you design your system in such a way that you can accommodate both from the beginning.
Got it, John. Thank you very much. We have another question from Micah. How much of the performance solutions or problems of the past are relevant with AI models?
I mean, the short answer is all of them, because AI models ultimately are running on the same compute hardware that we've been using for decades. GPUs have been around for a very long time. CPUs have been around for a very long time. And at the end of the day, those architectures haven't fundamentally changed to accommodate these new AI and machine learning workloads. Now, if you look at the really new stuff like the data flow architectures for AI accelerators, there are some differences there where you could have learned all the performance optimization techniques and skills in the world for CPUs and GPUs, and there's still going to be a lot more to learn and other things that you need to do for these newer models of computation. But for the vast majority of us, the active performance optimization is still very similar. It's still about measuring the performance of your system, identifying bottlenecks and pain points, and then thinking about how you can change your algorithmic approach to to reduce or minimize the performance impacts of certain pieces. And managing things like memory and data locality and operational efficiency. So all of the principles are still going to hold true. Many of the specifics when you deal with data flow architectures are going to be different, but software performance optimization as a mindset and as a process is basically unchanged.
All right. Yeah. Thank you. Thank you very much, Sean. We have another question on Valve, as we were talking about it a few minutes ago. Is Valve of any specific architecture now? And furthermore, can it be extended to any other architecture?
So right now, Valve is developed to be to enable portability. That's something I didn't emphasize here too much, but as the CPU ecosystem is diversifying, it becomes more important for application development to be able to pivot and cross execute on a variety of different platforms. So right now, Valve supports x86, ARM, and RISC-V, and the various vector instruction sets supported by each of those architectures. And certainly there is room to extend those as there are new entrants or new areas or markets that we might need to extend to.
Thank you. Thank you, John. And of course, we can learn more about Valve from our website. We have a few more questions. We'll try to accommodate and answer as much as we can within our allotted time period. Is Multicoreware involved in any open source projects which help improve software performance?
The short answer is yes. In terms of open source projects, I mean, we work on open source projects like compiler frameworks, LLVM, GCC, MLIR. Many of those are working on so for instance, the work that we did here on Halide, that in theory is open source. I don't think that the Halide upstream has taken our changes because, the Halide community overall wasn't prioritizing the DSP targets or environments. But in theory, all of that code is publicly available and would be something that we is upstreamable if the upstream community wanted it. And many of the projects that we work on are published academically. So they're publicly published in academic conferences where we describe all of the things that we did to improve and achieve performance, and you can do it too if you follow these methods or methodology. So there's certainly a lot of work that we do in the open on this area. But like I said, the much of the work that we do is enabling specific systems for specific silicon vendors, or developing high performance libraries that you can just license. And obviously, if you just develop a library and release it in the open source, there's not a lot of motivation or ROI there. But Multicoreware has a history of creative business arrangements to enable open source high performance software. The X265 video encoder is the prime example of that.
Thank you. Thank you very much, Sean. We have a few more questions. This is an anonymous one. Can you give us a few examples of tools for improving productivity, specifically focused in deep learning?
I already put in my slides, like there are the high level frameworks like PyTorch and TensorFlow were designed to be that. They're designed to be, high productivity environments for designing deep learning engines and systems. I would say this is still a very new area, and there is a lot of open space for new entrants and new models and new development for productivity in deep learning methods and environments. I think of the Mojo environment as something that is trying to be both higher productivity and higher performance, kind of shifting the curve in that area as something in the ecosystem that people are trying to improve. MLIR as a piece of infrastructure was meant to improve the productivity of developers that are working in that environment. But I would say there's not as much, especially for end users, people who are developing new machine learning models. I don't think there's nearly as much out there as for productivity tools as there could be. So I'm excited to see what development happens in that space.
Thank you, John. Thank you. We have one more question in the question and answer chat. Given a system, are there any machine learning models that can predict the maximum performance that could be achieved based on the complexity of the model?
Sure, there are definitely models that can do that. Given a model, it's going to have a certain minimum amount of compute operation requirements. And you can say if you got ideal peak performance on the system, what would that achieve? Like that's just a back of the envelope calculation that you don't even need a fancy tool to do. The real question is going to be, okay, what percentage of that back of the envelope peak performance will you actually be able to get, and how much work is it going to take you to get it? That I think is not well understood or supported right now. There's a lot of open space in that area as well to say, sure, you can do simple back of the envelope calculations to say, here's the peak performance that you could reasonably get. But in terms of what you're actually going to get and how much work it's going to take you, I don't think that there are very good tools out there right now for evaluating that. And that's something, like I mentioned, that we're actively interested in and working on here at Multicoreware.
Thank you, John. We also have another question from the Q&A chat box. Regarding your future NN productivity tool, would it be targeting on embedded NPU inference engines or ARM CPUs?
I don't know that I should say too much about that right now. I will say it certainly the most opportunity. If you're just looking at CPUs have an inherent disadvantage compared to GPUs and other accelerators in terms of peak performance. There's just a lot of overhead that you have to build into CPUs because there's a lot that we ask of them to run operating systems and very dynamic workloads, especially for CPUs that we expect to also handle general purpose computing workloads. So there's an inherent disadvantage there where I think there's just less opportunity to invest in tools to do CPU machine learning execution workloads overall. Really, the opportunities are in accelerators of various kinds, whether they're like embedded digital signal processors or GPUs or data center grade, PCIe accelerators.
Thank you. Thank you very much, Sean. We can go with one last question if it's all right with you. So what could be some best practices to be able to predict the productivity curve? So how do we know that we are focusing on productivity in the right area?
This is really hard to do. I don't know that there's a good answer to this question. A lot of it comes from, because this is not easily quantifiable, you need to talk with experienced professionals who have done this work and can tell you about their experience. Again, this is more akin to like social science research than, you know, collecting numerical data. So you need to talk with people who have experience with these systems to get an idea of what their experiences were and assume that, hey, their experiences are probably going to be similar to your own experiences. Your future experiences are likely to be very similar to your past experiences. So, in terms of getting at that information, that information is tied up in the experience and wisdom of professionals who have been doing this work for a long time. So talk with them, learn from them. This is more about wisdom than anything else. The other thing that I would recommend is be reflective. When you are doing work, take some time to reflect on the work that you are doing, because that will both give you the opportunity to question the way that you are doing your work, maybe identify ways that you could improve your own personal individual productivity. And also be reflective if you're working in a team environment, be reflective about what seems to be just the status quo and how everyone is doing their work, and be reflective of, are we doing things this way just because it's the way that we've always done things? Or are there new ways of doing this work? Are there new tools out there that are available that would make this work more productive or more efficient? So yeah, those would be my two pieces of advice. The only information that you're going to have is tied up in the brains and experiences of yourself and other people, but you're not going to be able to access it if you're not consciously reflecting on your experiences and doing that with other professionals.
Thank you very much, Sean. I am elated to say that we have quite a lot of questions remaining, but due to time constraints, we are going to have to conclude this webinar and this Q&A session. Rest assured, we're carefully gathering all of the questions posed here and answered, and we will share them with the audience here with the registrants along with the recording of our webinar in the upcoming days. John, I'd like to say thank you for this fantastic webinar and the engaging Q&A session.
Thank you all.
As we conclude today's enlightening session, our profound thanks to each and every single participant here. Have a wonderful day ahead.